Welcome to our today's lecture, wherein we are going to talk about the permeability through stratified soils. So, up till now, we have talked about the permeability of soil and how the water flows through the soil in the previous lectures. But you would have noted that in all the discussion that we have had so far, all our discussion revolved around water flow through a homogeneous soil or a single soil layer. But in reality, if we think, it is rarely the case that there is a single or a uniform soil which is present at a particular site. It is always the soil is always available in different layers. So for practical purposes, it is very important for us to see how the water flows through different layers, how the permeability of water can be evaluated when we have a more realistic scenario in which there is a layered structure. So this is what we are going to talk today, and this is our discussion topic for the day. So when we talk about the stratified soils, we have generally two cases. This is something that we have touched upon previously as well, that the water can flow in any soil either parallel to the stratification or perpendicular to the stratification. So let's look at the case of water flowing parallel to the stratification first and see how an equivalent hydraulic conductivity or an equivalent permeability can be evaluated for such a case. So let's consider an example as shown in this figure, where we have several different layers, which several different layers of soil. Now, let's assume that the water is flowing parallel to these layers. Now, once the water is flowing parallel to these layers, our objective is to estimate the equivalent hydraulic conductivity of the whole strata. Now, once again, I repeat that previously all we have been doing is determining the hydraulic conductivity of a soil where it was all a uniform soil. So it was all the same soil from top to bottom. But this figure represents a more realistic case in which we have soil 1, soil 2, soil 3, up to soil n, and there are different soil layers, and we want to determine that equivalent or the cumulative hydraulic conductivity when the water is flowing through these layers. So let's see how can we determine the hydraulic conductivity in these cases. So, so when the water flows through these layers, so what do you think will be the velocity of water in each individual layer? The water enters from this end and the water exits from the other end. Now, when the water enters from this end in soil layer 1 and soil layer 2 and soil layer 3, because all these three soil layers are different in nature, what do you think? The velocity of flow of water, would it be the same in these three layers or would there be any difference in them? Yes, as you might have guessed, that the velocity of flow of water or the speed through which the water is passing through each layer is going to be different. The simple explanation can be that this layer can be of sand and the second layer can comprise of clay. So because of the difference in the nature of the particles, so sand will have a higher permeability and the water would flow very quickly from this. So the velocity of flow would be more in this layer compared to the velocity of flow in the clay layer. Now, what do you think will happen with the hydraulic gradient? If we talk about the hydraulic gradient of each individual layer, we would realize that since the initial head of water is the same at the starting end, and the length over which this water is going to flow is also going to be the same through each layer. So the hydraulic gradient through each of these layers would also remain the same. Now, with these two basic fundamentals set, we can then proceed to see how the hydraulic conductivity how the equivalent hydraulic conductivity can be evaluated for such a case. Now, we have already seen this equation that the discharge is equals velocity times cross-sectional area. And we also, what we can do here is we can convert this equation into this form, in which this cross-sectional area has been converted into 1 times h. Now, h is, of course, the height, and this one represents the third dimension, which is into the page. So what we are actually doing is, since the water is flowing in this direction from left to right, so we want to take the unit cross-sectional area through which the water is flowing. Now this unit cross-sectional area would be equal to height times the height times 1, where 1 represents the third dimension, which is into the screen. Now, this equation can further be modified into this. We know from Darcy's law that V equals Ki. So replacing V equals Ki in this over here, we get this. Now, I've put H here, which H subscript H actually represents permeability parallel to the stratification. Now, if I ask you to determine the total flow, the total discharge through this layer, how can you determine this? Now, first, it is important to understand what we mean by the total flow. Total flow means the total quantity of water which enters from here and comes out from the right end. How can we determine the total flow of water through this entire soil mass? Now we know that because of the difference in permeability of each layer, it is possible that there is a different quantity of water flowing through layer 1 and a different quantity of water flowing through layer 2. So if I want to determine the total flow through the entire soil layers, what we have to do is we have to sum up the discharge through each individual layer. So how can we sum up the discharge? We are obviously going to make use of this equation, and by using this equation, we can sum up the discharge through each layer. So you can see over here, the total flow equals flow through layer number 1 plus flow through layer number 2 plus flow through layer number 3, and so on. Now, this KIH, that is the flow through each layer, has been evaluated using this equation. We can further modify this equation as on the left side, we can replace Q with KHIH for the overall strata. We get this, and we can rearrange the whole equation to get our final permeability in this form. So if you know this equation, if you remember this equation, you can easily determine the equivalent hydraulic conductivity parallel to the stratification. So what we have here is KH, which represents the equivalent hydraulic conductivity parallel to the stratification. You need to input the hydraulic conductivity of layer 1 times height of layer 1, which is here, plus hydraulic conductivity of layer 2 times height of layer 2, and so on. Divide it with the total height and you'll get the equivalent hydraulic conductivity. So this was how you can determine the permeability parallel to the stratification. In the same way, we can look at our second case, which is permeability perpendicular to the stratification. It is very likely and it is possible that water does not only flow parallel to the layers, but water can also flow perpendicular to the layers. So if there is a case as shown in this figure in which the water is flowing perpendicular to the layers, for example, as shown in this figure, how can we determine the discharge, or how can we determine the equivalent hydraulic conductivity in such a case? Now, in such a case, let's first of all look at what will be the velocity of flow and discharge through each individual layer. Now, what do you think? Compare it with the previous case. Now, in this case, what do you think? The velocity of flow through each layer and the discharge, would it be the same or would it be different? Now, in order to answer this question, let's assume that this uh, these different soil layers consist of different soil types. Let's assume that this is a sand layer, this is a clay layer, and we again have two more different sand layers at the top. So we have two sand layers at the top, another sand layer at the bottom, and a clay layer somewhere over here. Now you know that this clay layer is something, because clay layer has a very low permeability. So this clay layer is going to control the velocity of flow through all these layers. What I mean is that when the water starts flowing from here, water can easily pass through this sand layer, but this water is going to be blocked by this clay layer. Water cannot flow very quickly through this clay layer. So whatever is the velocity of flow of water in this clay layer, same will be the velocity of flow in this sand layer, and also same will be the velocity of flow in the other two layers. So because of this thing, the velocity of flow and also the discharge will be the same in all the layers. Now, what do you think about the hydraulic gradient and the head loss in case of these layers? In order to see the effect of hydraulic gradient and head loss, let's assume that we have installed piezometers at the bottom of each layer. Now, when we install piezometers at the bottom of each layer, the water level in each piezometer will rise, representing the pressure head at the bottom of each layer. As you can see from the water level of each piezometer, that as we are moving far away from our water source, there is more and more loss of head. So the head was maximum over here, but while the water was flowing through the first layer, it lost some of its energy. It lost some of its head. So this is why water level was slightly lower in the second piezometer. Now, if the water pressure or the water head is low, so it means that the hydraulic gradient in the second layer would be different compared to the layer one. And same would be the case in all the layers. So this is why the hydraulic gradient is going to be different in each layer. Now, if I ask you to determine the total head loss through all this layer, through all this soil stratum, how can you determine the total head loss? So you might think that if we want to determine the total head loss through each layer, what we have to look is we have to look at the head obtained in through each piezometer. So this water level in first piezometer minus the water level in the second piezometer is going to give us the head loss from this point to this point. Similarly, if I look at the head loss from this point from in this piezometer to the next piezometer, it is going to give me the head loss while the water was traveling from this point to this point. In this way, if I want to determine the total head loss, what I have to do is this total head loss can be determined as the summation of head loss through each while the water was passing through each layer. So this is how we can determine the total head loss. Now, we also know from the basic definition of hydraulic head that hydraulic head or the hydraulic gradient equals head loss over the distance over which the head was lost. For example, hydraulic gradient is head loss divided by the length over which this head was lost. Now, we by using this equation, we can write small h equals h times I, and with this, we can replace the value of small h, which is the hydraulic head, into this equation, and this equation will become like this. So you can see this total head then becomes as the summation of I1 H1, I2 H2, and so on. Now, we are interested in determining the permeability of soil perpendicular to stratification. Now, permeability of soil perpendicular to stratification, let's consider this as Kv. So this Kv represents the permeability of soil perpendicular to the stratification. Now, from Darcy's law, we know that V equals Ki. We can rearrange this equation, or we can rearrange this equation in terms of hydraulic gradient. And this hydraulic gradient we can replace in equation number 1. And our equation number 1 can become like this. So this equation can then further be rearranged in this form, and this is our final equation, which gives us the hydraulic gradient, or the equivalent hydraulic conductivity perpendicular to the stratum. So if we want to determine the hydraulic conductivity perpendicular to the stratification, what we need to do is we simply need to input our values in this equation, and we'll get the equivalent hydraulic conductivity by this way. Now let's solve a couple of examples to see how it is practically used. So the problem says, now these example problems have been taken from the book by Das. Now, a layered soil is shown in the figure here, in which H1, which is the height of the first layer, is given as 2 meters, height of the second layer is given as 3 meters, height of the third layer is also given, and also the coefficient of permeability in each layer is also given. Now, what we are required to do is we are required to determine the ratio of equivalent hydraulic conductivity, that is hydraulic conductivity parallel to the layer divided by hydraulic conductivity perpendicular to the layers. So how can we determine this? Now, there is one important point that I would want to make here, which will be helpful for you later on, that this KH does not always mean that this is the hydraulic conductivity in the horizontal direction. KH simply means hydraulic conductivity parallel to the layers. And KV does not mean that this is always the hydraulic conductivity perpendicular in the vertical direction. Rather, it is just representing hydraulic conductivity perpendicular to the layers. What I mean by this is something that you'll learn in a couple of more examples when we'll proceed further in this lecture. So let's determine the hydraulic conductivity parallel to the layers and hydraulic conductivity perpendicular to the layers. Once we'll find the answer, we'll simply determine their ratios. So in order to determine the hydraulic conductivity parallel to the layers, so these are the basic formula that we have to use. And to determine the hydraulic conductivity parallel to the layers, we can simply replace all the values in this equation. And by simplifying it, we are going to get the hydraulic conductivity parallel to the layers. In the same way, we can determine the hydraulic conductivity perpendicular to the layers. You just need to replace all the values in this equation, which are already been given here. You just need to replace all the values to determine hydraulic conductivity perpendicular to the layers. So here I've replaced all the values in the basic equation for the hydraulic conductivity perpendicular to the layers, and this is how we can get the required answer. Now, once we know this hydraulic conductivity parallel to the layers and perpendicular to the layers separately, what we need to do is we need to simply determine the ratio, which can be obtained this way. So what we get from here is that the hydraulic conductivity parallel to the layers is around 139 or 140 times faster than hydraulic conductivity perpendicular to the layers. Now, this is something that we have studied a few lectures back, that the permeability parallel to the stratification is always more compared to permeability perpendicular to the stratification. And from this data, it is also proved that permeability parallel to the stratification is much more, almost 140 times more compared to permeability perpendicular to the stratification. So let's solve another example and let's see. It's a very identical example to the previous one. So what I will actually do is I will not solve this one by myself. Rather, I will leave it to you to try and do it by yourself. Yeah, you're obviously going to use the basic formula for the hydraulic conductivity parallel and perpendicular to the stratification. And you are, and for your convenience, what I've done is I've put in the answer to this problem over here. So this is, if you are going to get an answer somewhere close to this, it means you've solved it correctly. So let's move to the next one. So this is an interesting one. This figure here shows 3 layers of soil in a tube that is 100 mm by 100 mm in cross section. So we have a tube here which is 100 mm by 100 mm in cross section. So this height is 100 millimeters, and the third dimension, which is into the screen, is also 100 mm. So it is like a square tube, which of the size. And inside this tube, there are 3 soils, A, soil B, and soil C, which have been put inside this tube. So if you notice, one end of the tube is higher, at a higher elevation, and the other end of the tube is at a lower elevation. So once we open up the tap from here, water flows from the top, it flows through these soils, and after flowing through the soil, it comes out, and the rest of the water drains out. So from this, we can also see that there is a constant head difference that has been maintained in this example. So because this water level cannot change, this water level over here cannot change, it will always remain constant because any excess water is going to fall down. Same is the case over here. So any excess water is going to flow down. So a constant head difference is going to be maintained. So water is supplied to maintain a constant head difference of 300 mm across the sample. The hydraulic conductivities of the 3 soils, soil A, B, and C, are also given here. So we are required is to determine the rate of water supply in centimeter cube per hour. So what we mean by the rate of water supply is that we need to determine the discharge through this layer. Now, how can we determine the discharge through this layer? So first thing is that we have to determine that which case is this. Is it the case of water flowing parallel to the stratification, or is it the case of water flowing perpendicular to the stratification? So it might appear to you that the water is flowing in the horizontal direction, but if you look closely, that the water is flowing perpendicular to the layers and not parallel to the layers. Now, if the water is flowing perpendicular to the layers, then which formula should we use? Yes, we need to use the second formula that we derived, which was for KV. As I told you earlier, that this KV, it might look as if it is representing the permeability in the vertical direction, but it is not the case. In actual, this KV represents permeability perpendicular to the stratification. Now, with this point, it becomes pretty clear how to solve this. So you have this basic information with you. You simply need to input all the data in this formula with H. This is the total height of the soil layer. Now remember, H represents total height of the soil layer. In our case, now this is the length of the seepage path. This is the total height of the soil layer. Now, what you need to do is, if you are still confused, you need to rotate this figure vertically. You need to rotate this figure by 90 degrees clockwise, and it will become exactly similar to the figure that we had used in order to derive this one. So this H is the total distance over which the water has flown, or the water has seeped through. So it is 450 millimeters. H1, H2, and H3 can easily be determined from this figure, so as K1, K2, and K3. You simply insert all the values here, and you can get the value of discharge. So this pretty much covers what we had to discuss regarding the water flow through stratified soils. So what I'm going to do is next, I'm just going to give you a quick overview of some of the importance or significance of the seepage studies. Why these studies are important. Let's have a look at that by using a couple of examples. So I'm going to share a couple of case histories with you. The first one is failure of a very famous dam, which was named as the Tendon Dam. Now, this dam, so this shows the initial figure of the dam. It was a newly completed dam which was opened in May 1976. So once the dam was opened, they started filling water in the dam. Now this is the downstream side of the dam. The water reservoir was at the back. Somewhere over here, you would store water. So once the dam construction was complete, they started filling the water. But the interesting thing was they filled water at a very rapid rate. They filled water at a rate of 3 feet per day. Means they were filling water in this reservoir in such a way that the height of water in the reservoir was increasing at 3 feet per day. Generally speaking, in today's world, we know that the rate of filling is generally controlled up to around 1 foot per day. So this was the initial image of the dam, which was, as I told you, which was opened around May 1976. And just around 1 month or less than 1 month, what there was started some leakage from the dam. As you can see, it is June 5, 1976, and some leakage started occurring here. Now, this leakage was observed early morning, and you can see that there is a dozer which was sent down to do all the repairs. Now, this timeline is important for you. You see, this figure was taken at around 10:45. The next figure, the next image I'm going to show you was at just around less than 1 hour after that. So in less than 1 hour, you can see the extent of this damage has increased so much. So what is happening is that there is a cavity that has been formed and the water starts seeping in from the upstream side. As I had told you earlier, that there is a water reservoir at the back. The water is stored at the back. So it's all filled with water on the back side. So, and this dam body is actually blocking the flow of water. So water starts flowing through the dam body and it starts coming down. So this was at 10:45. Now I'm going to show you the next image. At 11:20, it expanded, and the dozer which was coming down to do the repairs, the dozer disappeared in all the debris. And then in next 10 minutes, see what's going to happen. So this is at 11:30. Just 10 minutes after, it is further expanding, and this expanding continued another 20 minutes after this. Now you can see, comparison with the previous image, you can see that the hole is continuing to expand upwards. So it's a little downward here. In the next image at 11:50, you can see that it started moving upward. So it started moving upward, it expanded further, and at 11:55, so dam crest was reached. So this hole reached the dam crest, and once it reaches dam crest, you can also see here, notice here that the water is gushing out under pressure from the dam. So if you see that all this, the first leakage was observed around 7 a.m. The first image I showed you was at 10:45 when there was visible leakage, and within 1 hour, what happened to the whole dam structure. Now it's 10:45, it's 11:55, and this next image shows that the whole dam body collapsed. And because of the dam body collapse, there was a huge flood caused. You can see that this is the reservoir on the downstream end, and this reservoir, all the water is flowing towards the downstream, and a huge flood was caused because. This shows the present day situation of the Oroville Dam. There used to be a dam body here. The spillway is still intact, and it is here. So probably it serves as a recreational spot these days. The second case history I'm going to share with you is a very recent one, and this is of Oroville Dam in California, US. Now, this is the plan view of the Oroville Dam. Now, this dam body was there to block the flow of water from Lake Oroville, and this dam body is actually blocking the flow of water. There were turbines installed somewhere here, and we have a power station here. So water from the downstream end, it flowed through underground tunnels to this power station, produced electricity, and the water was thrown out towards the downstream. There was a spillway over here, which is shown here. Now, this spillway, when the power station had to be turned off, when the water cannot go out from here, or there are any repairs going on, the extra water, or maybe there is a high flood coming from the back end, the extra water would be drained out through this spillway. Now, besides this main spillway, there was a location for an emergency spillway over there as well. Now, there was a location of this emergency spillway, and this emergency spillway had around 30-foot high concrete wall. But this concrete wall was here, but this emergency spillway channel was not lined. It was just for emergency use, so they saved money and they did not line. So this is an image of the Oroville Dam in its glory days. So in around 2005, some local authorities, they proposed that this emergency spillway, it had to be lined so that if some problem occurs to the main spillway and they have to use this emergency spillway, so because this is not lined, so because of the unlined channel, it can have some problems in the future. But the government was not willing to invest money on it, and this plan was rejected. So they did not repair or improve the quality of the emergency spillway. So this was 2005. Let's see what happened in 2017. In 2017, February 2017, which was just 2-3 years ago, there was some collapse observed in the main spillway. Now, once there was some problem with the main spillway, then obviously they had to close this main spillway. And if they are closing the main spillway, the water which was previously going downstream from the main spillway had obviously had to go from this emergency spillway over here. But what was the problem with the emergency spillway? The emergency spillway had problems that it was not lined, and having water flow through it for a long time can have its problems. So they opened up the emergency spillway, closed the main spillway, and the water started flowing from the emergency spillway. But as it was feared, since this emergency spillway was not lined, so because of being unlined, this emergency spillway, there was a lot of erosion in the emergency spillway, and this got choked very quickly. Now, once this got choked, all the water started going back from the main spillway once again. And when the water went back from the main spillway, you can see the erosion in the main spillway, it increased. It did not only increase, but it also blocked the flow of water on the downstream end of this power channel. Now, once this water channel was blocked, because of blocking of water from this channel, the power station had to be turned off, and the whole dam operations was stopped. So they had to repair the emergency spillway, and because of the repairs of the emergency spillway, obviously the whole operation had to be closed for a long period of time, and a lot of financial damage had also to be incurred. So this shows a Google image of the whole dam structure. This is the failed spillway here, some emergency spillway locations, and the main dam structure. And it also shows some of the case history of the Oroville Dam. This is in its glory days when it was working perfectly. Then on 7th Feb, when it started eroding, and the erosion expanded after the failure of main spillway. So I hope with these examples you would have got a better idea of the importance of the seepage studies. That's it for the day. Thank you very much.